Hello students, so today we will take up a very important material. It's called silicon carbide, SiC. Now, uh, there has been an increasing demand for high performance materials which can withstand severe conditions such as abrasion, high temperature, pressure, atmosphere. So this silicon carbide has got the following properties which makes it applicable in severe conditions, and it has got various applications. It has the properties of abrasion resistance, and it can be stable at high temperature and in pressure, high temperature, high pressure, and in also an atmosphere of severe conditions. So it can withstand, which makes it applicable in various areas. For example, it is applicable in high temperature heat engines, it is applicable in nuclear fusion reactors, applicable in chemical processing industry, and aeronautical and space industries. Now, so silicon carbide has got properties of superior properties of superior oxidation resistance, then it has properties of superior creep resistance, it's got high hardness, and good mechanical strength. Then it has got very high Young modulus, and corrosion and erosion resistance. And it is relatively low weight. Now, let's try to understand how silicon carbides are prepared. First of all, we will first take up with a very important aspect of silicon carbide preparation, that is called sintering. Sintering is when the silicon particles or any ceramic particles are brought together at high temperature and pressure, and the particles start to coalesce and form solid particles from powders, and we get high density particles. Now, it has been observed that the powder compact of very fine pure crystalline solid does not densify during heat treatment without any applicable pressure. So that is why the pressure is equally important than temperature. So while preparing ultrafine particles of silicon carbide, considerable attention because of these powders after sintering of physical and chemical properties are kept into consideration. So what we do is, while preparing the silicon carbide particles, there are two principal factors which needs to be controlled. The first one is the ratio of the weight of the metal balls grinding media. Suppose we are using grinding for preparation of silicon carbide particles, and so the ratio of weight of the metal balls of the grinding media to the total weight of the particles to be processed. And the second condition is that the semi-fluid versus viscous characteristics. Semi-fluid, or we can say viscous characteristics of the grinding media. Containing the fine particles. Now, preparation of nanocrystalline alpha silicon carbide particle for studying the synthetic mechanism is a very difficult problem. So the properly distributed nanocrystalline particles with very narrow range of grinding necessitates a proper understanding of the process of grinding of silicon carbide. So what happens is that at the initial stage, the formation of large cracks which get developed in the original particles propagate. Now smaller particles with very fine have got very fine cracks, and the probability of the particles having cracks, these decrease. Probability of particles having cracks will decrease with grinding, leading to generation of strong particles. So we grind it, so we keep on grinding it, the cracks, particle cracks actually tend to decrease. However, grinding is actually done to reduce the particle size. So reduction in particle size means there's a probability of cracks are less. Another factor that we should consider while grinding, so we can consider it as particle 3, is the time of grinding. How much time you are spending in grinding, which also needs to be controlled to obtain the nanoparticles. Okay, now once we have prepared the nanoparticles, the purity of the nanoparticles is very important. Like the commercially available alpha silicon carbide is made by a process called Adhesion process, in which a mixture of sand and crushed coke with common salt and sawdust electrically heated. So we have a mixture of sand and crushed coke with common salt and sawdust. Take a mixture of the following, and then they are heated in a resistance. So there is electrical heating, and in a resistance furnace. And the temperature is greater than 26 degree centigrade. The reduction reaction of the high-graded silica results in silicon carbide. So the reaction is the following: SiO2 silica plus carbon 3C gives you silicon carbide plus carbon monoxide CO. Now, the reason this sawdust is added is for the to increase the porosity of the material. So, by increasing the porosity, what we do, we increase the circulation of the reacting gas. Reacting gas. So what it will do, it will actually remove this carbon monoxide formed. Now this alpha silicon carbide obtained from adhesion process is also has got some impurities, and while these impurities have negative effect on the sintering of silicon carbide, and moreover the silicon carbide formed through this adhesion process have got lumps and grits. Apart from that, the silicon carbide which we actually get, it also contains some amount of carbon which has not reacted with the silica, and so there is a mixed carbon in it. So that is why a purification is essential to remove the impurities and to make the nanocrystalline silicon carbide less sintered. So next we come to the sintering of ceramics. So after this adhesion process, the necessity of the sintering analysis because of the impurities present in the material. Now silicon carbide is a refractory material. Silicon carbide is a refractory material. This has got high temperature, high melting point. It can withstand high temperature, and they are also brittle, lower pressure resistance. So they pose problems in their preparation. While metals and polymers are melted and casted and sometimes machined to get right type of dimension. That is why getting the right dimension is difficult in case of a silicon carbide. So the preparation of ceramic materials mainly consists of grinding, as we have discussed previously. We grind it, and the raw materials, then you mix it with suitable binders. Pressing into different shapes. Then different shapes can be made, different shapes by pressing. And so these are, before any shape has been formed, these are called green bodies. So here the density is very important to obtain the final sintered product. After this stage has been complete, they have to be fed or sintered at sufficiently high temperature to get desired phase transformation. For phase transformation, that means what type of phase we are requiring. We need to increase the temperature of the material so that that exact phase is reached. So what is the microscopic driving force for sintering? We can say that the reduction of the excess energy associated with the surface is the main driving force. So sintering driving force is reduction of excess energy associated with the surfaces. And this reduction in excess energy can be taken up by two processes. So the total surface area, it gets decreased by increasing the particle size. That means when the particles coarsen, the total surface area getting decreased. And the second is that the solid vapor interfaces are eliminated with the creation of grain boundaries. The creation of grain boundaries, and which is followed by grain growth, leading to densification or sintering. For an effective sintering process into solid nanomaterial, the mass has to be transferred mainly by three different atomic diffusion. So we can say that for
हेलो टीचर्स, क्या आप भी फ्री में ऑनलाइन क्वेश्चन पेपर बनाना चाहते हैं? क्या आप भी एग्जाम से पहले
there has to be a mass transfer mainly through three atomic diffusion mechanisms. The first one is surface diffusion. Second one is the volume diffusion, and the third one is the grain boundary diffusion.